great. Got a recording going. Was about 45%, but that's decreased because we were offline for several weeks. So now we're at cumulative for O4B about 31% of the time. And this is a plot from back last July through current, showing the increase in detector sensitivities, showing that Virgo has recently come online at the start of O4B, and that there was this big pause for the Hanford interferometer needed to vent to fix some in-vacuum equipment failures, and that Virgo was able to readjust their schedule and come and do their maintenance at the same time as Hanford rather than waiting until September. I'll start now with the various observatories, starting with Kagra. During O4A, the observation period, their sensitivity was about 1 megaparsec. So that sensitivity is well understood, and we've got paths forward to improvement in all areas. So it seems like they've got definitely an achievable goal of hitting their sensitivity target of about 10 megaparsecs for when they rejoin the O4 run. The O4 run rejoining was significantly delayed, however, due to this once per century earthquake that happened very near the observatory. So this is just some graphics from their update that they gave to the LVK in March. But there was an earthquake epicenter on a peninsula here, and this is a zoom in of one of the islands in Japan where the observatory sits in this white circle here. So it was a magnitude 7 earthquake, very, very close to the observatory. Based on the seismometers that we have in the mine at the observatory, they estimated it was equivalent to what it would have been a magnitude 3 earthquake in the detector. And there's some pictures of, clearly there was a little bit of disarray. Since this is all underground, they had to do a lot of safety inspections before even beginning the repair work. But the team at Kagra has worked really hard and really impressively quickly, and they have done an enormous amount of work repairing about half of their in-vacuum mirrors needed attention, but all of those repairs are now complete and commissioning work is again ongoing. So that's been very successful given the significant setback that Kagra had due to this once per century earthquake. Turning to Virgo, this is primarily information about what they did during this brief break. Two kind of key maintenance and repair tasks were undertaken. We have auxiliary lasers. It happens that both LIGO and Virgo use CO2 lasers. These are critical to maintaining the shape of our mirrors so that we can maintain control of the mirrors. And the CO2 laser at Virgo, so it's this laser in the photo, we can see over time was significantly decaying in power, and within a few months would not have enough power to successfully keep the Virgo interferometer online. And so this did need to be replaced. So they got that done during this maintenance time. The other item they did was they, in vacuum, added a remotely controllable optic that has allowed them to study the dependence of the detector noise on the polarization of light at the output port, and very importantly, excluded one of the prime candidates for what is this excess noise at Virgo. So now that we've got this optic installed and they've begun studies of what happens when they actuate this optic, we can exclude this noise type, which was a prime candidate, and allows us to investigate further noise types and work towards other paths to increasing the Virgo sensitivity. So this is a big success that they were able to do that so very, very quickly. The Virgo duty cycle, I won't go through all of these different items of what makes up the duty cycle, other than to say this 10-day detector work in July came out to about 6.25% of time. And if we exclude that 10-day stop, then we've got about 80% of the duty cycle is online and observing. So a really exquisite duty cycle. Turning to Hanford, this is in two parts. Some of the work that we did in February. These are photos of inside our vacuum system in the input arm. We had found throughout O4A that coupling of the HVAC system, just the observatory building, air handling system, and other vibrations were coupling into the gravitational wave signal because this baffle was at an angle that was too small. And so some of our crew is here modifying it to change the angle that it sits in the system, and then also installing some other baffles to make these small spots less shiny and less candidate for stray light to couple into the system. So if I go to the next slide, this is a view where the camera is looking in infrared and the camera is being held in the beamline. So it's kind of like if you are the laser beam looking to see what stray light or scattered light could be problematic. The view from before, you can see there's some shiny pieces and this whole kind of system is glinting a little bit, even just kind of the bulk piece of this ring. Whereas afterwards, adjusting the angle to a better angle and also installing some more baffles, this is much more dark. So there's less stray light that can couple into the interferometer. This is a picture showing the work that we did in July during the urgent repairs. So in late April, we had one occurrence of something happened and we knew it was bad and we didn't know what it was. We did know that if we moved the main laser beam in the output arm going towards the final photodetectors by a few millimeters, we could recover sensitivity. And so we recovered and ran between April and early July with the main laser beam having been moved sideways a few millimeters. And then whatever had happened in April happened again in July. And since we, after this, were not able to recover control of the interferometer, bring it back online successfully, that caused an urgent need to understand, we could have moved the laser beam maybe one more spot, but we only had one more candidate spot, and we did not understand what was going wrong. So that created an urgent need to understand the failure mechanism and mitigate it. As soon as we opened the vacuum system and started taking a look, there were 5 different optical components that could have been a problem. Once we opened the vacuum system and laid human eyes on it, it was clear that this optical component clearly does not look pristine and looks awfully suspiciously like it's got 2 damage points side to side from each other. So once we understood that this was the problem, we still don't know why this happened, which is a concern, but we were able to put in a spare optic, and the optic next to this one got a bunch of the spatter and spray from this melted crystal. This is a KTP crystal polarization selecting optic. And from these ablations and craters, the optic next to it also was damaged. So we also replaced that optic. That went successfully and smoothly. It takes several weeks to pump down to ultra high vacuum, but within 4 days of having the vacuum system available, we were back observing. So we started observing on Saturday this week, where now is Thursday. So that was very good. Livingston, this is work that they did during the main planned commissioning break between O4A and O4B. Livingston did not go offline during this urgent break, so we've had an eye on the sky through July and August. They did some work cleaning their end mirrors. They've also done some work, so with this cleaning of the end mirrors and some other increasing the input laser power, they've increased the laser buildup in the long arm cavities, which increases the sensitivity that we have at higher frequencies. They've also, during that February-March break, did some damping, like by putting pieces of rubber in next to some of our in-vacuum components that were then able to reduce transient noise from other kinds of scattered light. So this plot shows a before and after of when the team shakes some object on the outside, changing as a function of time what frequency is being shaken. Beforehand, when it hit a certain resonant frequency, this is the main gravitational wave channel, would see an enormous amount of transient noise. And so that means that if any random vibration happened in the building and happened to be at this frequency, the gravitational wave channel would be polluted with this kind of transient noise. And, that's a repeatable thing. After doing the mitigation, you can do the same shaking outside, and now we no longer see that pollution of transient noise in the detector. So that was also very, very successful. I'll turn to updates on our low latency infrastructure. Soon, okay, I wrote at the start of September, but there have been some complications, so I'm not sure precisely when in September. But the LIGO Virgo Kaggle collaboration has a host of compact binary coalescence search pipelines, as well as unmodeled burst search pipelines. And one of the compact binary coalescence pipelines has been offline for a few months because it needed to do some upgrades. So that is soon to come back online. And then similarly, we will soon, at the same time, it happens that we'll just start those at the same time for other reasons, just coordination reasons. We'll operate a new burst pipeline search. Sorry, just looking at the time. And so those will come online soon. A reminder that the Virgo data is being used for sky localization and parameter estimation. But except for the GST-LAL and soon SPEAR pipelines, we're not using it for selecting candidates. The other CBC pipelines select candidates based on the Hanford and Livingston information. But all of the pipelines do use the full set of 3 interferometers to understand the parameters of the astrophysical object. And this is our best so far localized object. From June of this year, binary black hole, and you can almost not even see the sky localization spot. So the 90-degree probability area there was 5 square degrees. And this object was estimated at about 1.4 gigaparsecs. So that's all going well. I won't spend time on this other than to say the rapid response team, we do human vetting, as you know, of all of our significant events. And these are both the y-axis, how much time it takes us to do that human vetting. The x-axis for one of these is what day of the year is it in O4B. The other is all of them together, what time of day is it in UTC. Our average is better than 40 minutes, so less than 40 minutes of response time, which is well under our target. So that's great and going well. I'll flip to this to say that we are continuing to make public alerts. The rate of public alerts has certainly increased relative to O3. I didn't draw a line to guide the eye on this plot, but there is an inflection point here and the rate has increased. This is cumulative number of detections that we've made over observation time. So excising the breaks and just smashing together our observing runs. So including the preliminary candidates that we've found online, we've released a total of 212 candidates so far, which is great. As a final slide, this is on the Observing Plan website, so not news, hopefully, to most folks. But we do not plan any further breaks in observing for 04. And the current plan is that 04 will continue through June 2025. I believe the specific end date is the 9th of June. So obviously this can change if we have another equipment failure, but this is the first time we've ever had this kind of equipment failure, so I'm very hopeful that we won't have any further need for urgent breaks. So no further breaks are planned in observing for the rest of 04. And with that, I will conclude and pass the baton back to Curtis. Thank you.
Yeah, thanks. We have a few minutes for questions, so either raise your hand in the Zoom chat or you can use the chat. All right, Yair, go ahead.
Yes, thank you very much for this update. Can you remind me the new pipeline you mentioned, SPEAR, that's for the pre-merger alerts, or is that just for regular alerts as well?
The SPEAR pipeline, first I'll say that it was running for all of 04A, so it's just turning back on a pre-existing pipeline that hasn't been running for the last few months. It actually does both regular compact binary coalescence alerts, as well as it does have capabilities for the early warning alerts. But we have had running for all of 04A and all of 04B other search pipelines that are capable of doing the early warning alerts. So by having this one pipeline offline, we have not lost, we have continued to maintain our ability to issue early warning alerts through, I think, the GST-LAL and MBTA are the names of the pipelines. But I invite you to look, if I go back to this page, the EM follow user guide that we've got has further details on which pipelines are capable of both the kind of regular compact binary search as well as the early warning searches.
Thank you.
Any other questions? All right. Well, thank you so much. That was really great. So next we're going to move over to Igor and Fed. We're going to talk about Rubin Observatory, the MMA planning, and TOO follow-up plans.
Thanks, Curtis. Can you hear me well and can you see the slides correctly?
Yes, they look great.
Awesome, thanks. And thank you to the SCiMMA team also for inviting us to present today. My name is Igor Andreoni, and I will be talking about work that is really being carried out by thousands of people over the years, and maybe more than 100 interested in multi-messenger astronomy in particular. I will highlight the role that Federica Bianco and Raffaella Margutti had to push for this science case, among many others. And first thing first, Vera Rubin Observatory is dedicated to Vera Rubin. So there is a strong encouragement for everyone within the Rubin project and outside the Rubin project to just use the Rubin name when referring to the observatory instead of the acronym VRO. And you can also refer it as LSST, as in the main project that will be carried out at the observatory, the Legacy Survey of Space and Time. So just real quick, what is Rubin Observatory? Is a telescope with a very powerful imager. At the end of the 10-year LSST survey, once all the images will be stuck together, this is pretty much what we expect most of the southern hemisphere, the extragalactic part, to look like. The total, the final magnitude will be beyond 27, which is quite staggering. The resolution will be good. There will be multi-filter observation options, and the field of view is large, about 10 square degrees, which makes it very suitable for gravitational wave follow-up. And like Federica will show you later, there has been a lot of progress in the construction. It's been more than a year that the telescope mount moves. In this video, this is a real video, not an animation, and it is the actual speed of slewing of the telescope. So a lot of tons moved in little time. Some very recent highlights from these years: that the camera made it to the summit safely, the mirror coating was completed, and even the secondary mirror was installed. So the project is truly getting close to first light. And just to put Rubin capabilities a bit in context, probably many of you have already seen this field of view comparison among some of the maybe most popular, most known imagers out there. And just to make a comparison in depth as well, say with comparing Rubin with the Zwicky Transient Facility, in 30-second exposure, an imager mounted on a 1-meter telescope typically reaches about 20.5 magnitudes, while Rubin will go as deep as beyond 24th magnitude. So how does that translate in volume that it will be probing? Say you choose a peak of a fairly standardizable source like type 1a supernovae, the volume that you explore is almost 10 times larger than what some of the current wide field survey are capable to do. So this means that Rubin will be able to explore the depth of the sky in the statics and in the time domain like never has been done before. Target of opportunity observations have been discussed in many papers over the years, starting also with Phil Coppert-White work and other people who mentioned them. Probably the first time that the community really came together to propose a strategy for TO observations in which the normal operations are dropped in favor of slewing to follow up gravitational wave and other events. All of this was in 2018. It's part of this white paper that Raffaella Marcucci has led. And over time, first of all, O2 happened, O3 happened. So we managed finally to, I think, improved a bit the strategy in a more informed manner, although the changes are small because of the good work that theorists did in making their predictions. And you can find this more updated paper published in Astrophysical Journal Supplement as part of a special issue for which Federica Bianco is PI, that was published starting in 2022. Quite recently, we tried to further pull the community together. In this case at UC Berkeley, we held a workshop in May of this year. And the objective is, instead of collecting a bunch of additional white papers and then have a committee evaluate them, just be there in person or remotely. We try to make it as hybrid and functional as possible to provide a community recommendation to a committee that will tell you in a second regarding TOOs with Rubin. So gravitational waves, but not only. And this was supposed to be an actual workshop. So most of the time was spent in thinking of strategies and writing text. So thank you to everyone who contributed. The link to this report is available online and will be published on arXiv soon. The report was meant to go, not quite to the directors yet, but to the SCOC, the Survey Cadence Optimization Committee, made by this bright individual who are top scientists in their own field, and they're tasked with coming up with an official recommendation for the directors for what the survey cadence and Rubin operation should look like. They don't have the final say, but they are the most prominent organism that the community has to advocate for the survey cadence. So a quite exciting update from July is that the SCOC has voted on the recommendation that we provided in the report, and unanimously. And this is basically what will be put forward as the preferred way to do TOOs with Rubin. So once again, you can go on the website of the workshop, and you can see a link that you can cite already, but I expect by the end of September the report to also go online on archive. The science cases that were covered as part of the report are multiple. Quite a few involve gravitational wave science as part of the multi-messenger broader topic, from maybe the more popular binary neutron star and neutron star black hole mergers to gravitational lens systems. Some people were particularly interested in a binary black hole follow-up. And also we wrote a few paragraphs on unidentify and model gravitational wave sources and possibly even lens GRBs for the future. But again, the scope of the report is much broader than that. I know that is a very bad idea to put tables in talks, at least this is what I heard. I hope you don't mind me doing it once, just to show one more time in the context of kilonova discovery and GW follow-up, what the capabilities of Rubin could be. So here you have in black the depth, especially if you check the two middle columns, the absolute magnitude that you can probe with 180-second exposures, in blue with 120 seconds, in orange with the standard 30-second exposures. The takeaway message here is that you can definitely detect a kilonova like GW17817, which peaked at absolute magnitude about minus 16.5 or so. But also you can probe fainter models, obscure kilonovae, or kilonovae that happen in binary with perhaps a more equatorial viewing angle compared to the observer, thanks to the depth that Rubin can get, even up to 700 megaparsec. And in this slide, I'm just flashing a couple of light curves for kilonovae. In the upper case, a brighter one at 350 megaparsec. In the lower case, a fainter kilonova model, still at 350 megaparsec on the left and 700 megaparsec to the right. We should be able to see the kilonova that far, and in most cases, even probe its temporal evolution. So luminosity and color evolutions, which are key to distinguish real kilonova candidates from most of the other known transients out there. Going a little bit more in the nitty-gritty details, people decided to divide especially neutron star, and neutron star black hole mergers into gold events or silver events, depending on the area of the 90% credibility region, the integrated probability. And we may expect in 05 up to about 16 of such mergers to be very well localized, and perhaps 6 to be followed up in the regime in which the SCiMMA is larger than 100 square degrees and it's smaller than 500 square degrees. And as you can tell from this figure, the strategy is ideally, especially for the well-localized events, to have up to 3 returns on the same field over the first night. So this is a log scale that you see on the x-axis, possibly in 3 colors to have a strong handle on the temperature and possibly catch the blue component, and then later continue the follow-up for up to 3 more nights in at least 2 filters, so that we can once again do photometric classification and find the true counterpart, even if we don't manage as a community to take spectra of all the candidates that Rubin will reveal. When it comes to lens binary neutron star mergers, the idea here is to follow up those events that have very high probability of being in the mass gap, meaning that at least one of the components is between 3 and 5 solar masses, but at the same time is unlikely to be a neutron star black hole merger because of effect due to the redshift. This is the regime in which we may expect lens binary neutron star mergers to live as gravitational wave signals, and basically by monitoring the area of interest with Rubin going as deep as possible should allow us to distinguish such a signal from contaminant sources and possibly get invaluable spectra with JWST. When it comes to binary black hole mergers, the main models out there, among others, literally dozens that exist now in both jets, they require the merger to happen in the disk of an AGN for a bright counterpart to be present. There is at least one candidate that was published in Graham et al. 2020 paper, and others may be lurking out there. So in short, the idea here is to have TOOs for binary black hole mergers as soon as possible to probe the shorter timescales. And from there, go observe the fields again and again in log space time intervals, and then complement this somewhat natural cadence with the regular LSST survey. How will, you may wonder, how will you be able as a community to access possible counterpart candidates? So Rubin Observatory is geared up to do full real-time analysis, in particular image subtraction. So difference imaging analysis will be performed possibly in less than 60 seconds. So a lot of computing power is going into it. And something that is important to notice is that all the candidates that will be packed up as alerts for each image in which they're found will be public to everyone in the world. And they will be distributed thanks to brokers. There are 7 LSST brokers. You can find the names in this slide. And here I just put an example for Ample, as per many others, just to show a little bit what brokers do. They take the real-time alerts, they do something that tend to be a bit different from broker to broker. So it's good you go shop around for what's more suitable for your favorite science. You can match them with simulation, archival information, and then distribute an output to the community. And a similar schema you can find for Alersi, Laser, and all the other brokers. So this is information that is available truly to everyone, even those in countries that don't have direct access to the entirety of the Rubin dataset. A quick update on the availability of resources, such as the survey strategy website. If you want to know more about what the LSST survey will be about, feel free to go to survey-strategy.lsst.io. There is also a link to target of opportunity observations. There is just a sentence or two at the moment, but will be richer in the future. And for those who are working in countries with full access to the Rubin dataset and resources, you can also use the online portal, notebooks, and APIs to access even more resources, for example, to complement what you can get from the alerts. And I strongly encourage you, if you have any feedback about these resources, reach out to the Rubin Users Committee. You can find quite easily all the contacts online. And as per the timeline, it's coming soon. The first photon is expected to come in January 2025. This means that Rubin will start collecting photons, maybe with the commissioning camera before the LSST full field of view camera, well before the end of 2004, thanks to this extension. So stay watching this space, because we may get observation of gravitational wave sources with Rubin, even without waiting all the way to 05. If you want to know more details, go to ls.st/dates. I will leave you with my summary, and I'm happy to take any question before Federica shows a couple of recent pictures.
Thanks so much, Igor. Any questions? Again, you can use the raise your hand or you can post in the chat. All right, Patrick, go ahead.
Hi, Igor. Thanks. Very nice presentation. I wanted to just check on your slide about well, actually, even here, these triggers and so forth. What are those trigger rates based on? Are they pre-04 estimated detection rates, or are they updated to include what we've gleaned from 04A and part of 04B?
Yeah, I think they are the most updated rates from Michael Kopflin's group, and basically the ones that Weissman has published more recently. So those should be based on realistic simulations of the observing scenarios. This is what we used as baseline for the rates. And to you, or if anyone else would like to use different rates, basically you can just scale up and down or down from those rates that we have used in the paper.
Yeah, that actually sounds great. I will just, the reason I ask is, of course, we know that the actual detection rate, for example, of BNS is significantly down compared to what you would have believed at the start of 04 when the Weitzman paper was published or was written. And the other thing that's probably going to be true, although I think there's still uncertainty, we don't know the answer, won't know the answer till next year, is the localization and the fraction of well-localized objects. So just a little remark on that.
Thank you, Patrick. We are aware of that, sadly. We were hoping, obviously, everyone in higher rates, but we thought it would be a good idea to work with published numbers and have a solid handle to present to the SCOC. And then the plan is on a yearly basis to just review everything that we have said in terms of strategy, in case kilonova looking very different show up, or in case the rates have to be substantially revised. But we still have a good bucket of time that maybe we can allocate to more poorly localized events so that we can find at least several counterparts during 05.
Rafaela, did you want to add anything?
Yeah, I just want to remind that these are not the rates of everything that we will find. So we are not planning to go after every single merger that LIGO, Virgo, Kagra will find. So those are selections.
Any last questions? Igor, why don't you start letting Fed transfer over?
I think Igor really just said everything that there was to say. I just have some photos for the sake of entertainment, since I was just at the summit last week. Let me see, share. I was just at the summit last week, so let me show you some images to demonstrate that what Igor said is real, like things are really happening and happening fast at this point. This was not last week, this was in 2019, the last time I was at the summit. It's been a while. Usually it's advisable if you're building an observatory to have your dome solid so that weather doesn't interfere with your observations. So now we have a dome. There's a telescope mount assembly that is functioning, as Igor pointed out. And not only that, but we just mounted the M2. So this is me. And this is way in the back is the M2. So this X structure will then go away. It's a counterweight that has the same weight as the M1, M3 mirror, which we're gonna mount soon. When that happens, you will not have visibility of the M2. So this was a one-in-a-lifetime shot that I could take a photo of myself and my reflection on the M2 mirror, which is mounted. Do you see the camera as well is ComCam. ComCam is much smaller than LSST COM, but it is the same physical size. It's a much smaller field of view, but it's the same physical side and the same physical weight, because that way we had the right weight on the telescope to make it work for commissioning. So a couple of other images. So this is from the abstract from the paper that Igor referred to. You can also find the paper at the convenient link ls.st/to while we wait to post it on the archive. And a quick summary of the number of hours that we're going to devote to TOs. I want to emphasize that LSST at its conception was strictly designed as a survey telescope, not as a PO or response machine in any way. So this is a significant departure from the original plan for LSST to allocate time to target of opportunity responses. But the system is capable of adapting the scheduler in real time, so there's no reason why we wouldn't be able to do TOs. And obviously the scientific return is expected to be enormous. And so the Rubin Observatory at large, the Survey Cadence Optimization Committee is very enthusiastic to enable target of opportunities with TOs. The fraction of time that we will spend on TOs is capped to make sure that we don't interfere with the wide, fast, deep, the main survey of LSST, to about 3%. But that's not a small number of hours, because that's a 10-year survey that will have a lot of hours. So we expect to spend nearly 300 hours on TOs from gravitational waves, 6 to 18 hours on TOs from neutrinos, and up to 30 hours on TOs from solar system objects. And I can show you here some quick simulations of how the responses to TOs that we obviously made up, TO triggers that we made up to reflect the characteristics that were described we should expect in the paper that the community wrote at the Berkeley workshop. So this is the response to gravitational wave binary neutron stars, neutron star black holes, black hole black holes, and also unidentified gravitational waves that we might encounter. This is the specific, quite different strategy that we would adopt in the case of a lens binary neutron star. I think we're simulating a few lens binary neutron stars. The event rate is a bit lower, but we wanted to simulate both the response with a large localization area and the response with the small localization areas. Neutrinos look rather different. We can typically respond to a neutrino alert with a single pointing. Our field of view is nearly 10 square degrees. And solar system objects yet look rather different. And I'm bringing those up. Well, neutrino obviously is MMA, solar system objects is not, but I'm bringing those up as well because while O5 will start well into LSST, we can start responding to neutrino triggers and solar system triggers right away as the survey start. Thus we can test the system and see that we can then be ready to respond to gravitational wave triggers when O5 starts. And you've already seen the recommendation of the SCOC, the Survey Cadence Optimization Committee, that is giving recommendations on the survey directly to the Observatory Director, Bob Blum, has already endorsed the paper and recommended the implementation of the TO program as per the paper. But let me emphasize that we are also recommending that another workshop, similar to the workshop we held in Berkeley, is held closer to O5, precisely to update rates and strategies with better knowledge of how the O5 system will work and yet better knowledge of the rates of events. And finally, what needs to happen next? Assuming that we're going to ingest alerts from SCiMMA, we need to work with SCiMMA people to develop the tools that can allow us to pull the alerts to the summit. Once we have that infrastructure in place, the Rubin personnel is in charge of turning the TO paper into an actual algorithm that interacts with our scheduler and responds to the triggers. And very, very, very optimistically, if we put all our ducks in a row right away, and if commissioning goes well for all the other aspects of the survey that we need to get ready during commissioning, we might be able to just start responding to alerts before the end of 04 with ComCam, with very little probability of detecting a counterpart, because ComCam doesn't have the large field of view of LSST, but just to demonstrate that we can do that in 05. And this is a photo of LSST that now looks like a real observatory, because it is, you know, all there over the beautiful Chilean mountains. It's remarkable what fraction of those mountains are actually owned by Aura. And it's a beautiful view, I think.
All
That's
right. Thanks so much, Fed. We're running a little short on time, so Sarah, if you want to start putting up your conference announcement, why don't you do that? And while she's doing that, if anybody else has got any more quick questions for Fed or Igor, now's a good time. All right. Yeah, if you have more questions, feel free to email around. So Sarah.
Hello, everyone. Yes, so thanks for Gautam to ask me to come here to announce this conference. We are really excited to announce this conference that'll start February 2nd and run through February 7th next year at Aspen. And the whole idea of this is that we are starting to detect what we believe is the gravitational wave background down at nanohertz-frequency with pulsar timing arrays, and dreaming onward from that. If this is the background from supermassive binary black holes, as it is expected to be, then it's likely to be followed by continuous wave detections. So we're hoping that this conference will be a really great meeting of minds between people doing, you know, MMA infrastructure, pulsar timing array interested people, and electromagnetic wave people who study, you know, the binary supermassive black holes, and also theorists. So we really encourage many of you to come. We want people who want to think about how to design and adapt existing surveys towards, you know, supermassive binary black hole studies. I think there will be a lot of overlap between what has been done for LIGO in terms of cyber infrastructure and, you know, survey planning and pulsar timing arrays going forward. So we're looking forward to see you there. The process is that you will actually have to apply. Oh, I should say, you know, this is our wonderful scientific organizing committee. Some of them are on this call. You have to apply through the Aspen website. I will link this conference in the chat in a second. And I think we have a cap at maybe 110 people. But regardless, apply, and we are looking forward to see you there. Thanks.
That's great. Thank you so much. All right, we're running low, so Chris, let's talk briefly about SCiMMA, and then we'll try to get the GCN as well stuck on the end.
Okay, so I think in the interest of time, Gautam has suggested we should move the actual demo of the SCiMMA stuff to the next call. So we should maybe just say right now that, you know, as noted, SCiMMA has taken over the responsibility for operating these calls, and we have integrated together the old OpenLVEM accounts with our identity management system. So it should be possible to manage things related to, for example, subscribing to the mailing list through our infrastructure, and that is generally working. Do you think there's anything else, Curtis, that we should go into at the moment, or?
No, I don't think so. I think that's great. What I was going to just say is, if somebody is not on this call who you think should be, and then because they didn't end up on a mailing list, do have them go through the SCiMMA website and subscribe to the email list. If you have any issues, by all means, please reach out, because we will fix any of the issues that we run into. Great. And then Judy and or Leo had like 3 minutes about GCNs. We'll also do probably a longer talk in upcoming meetings about this as well.
Yeah, I'll take that. We just have a couple announcements to go through. So on our website, if you, in the banner here, you click news and announcements. By popular demand, there is now a heartbeat topic called gcn.heartbeat. So if you subscribe to that, you'll get a little test message once a second, and it looks like this. It's just a simple JSON packet. GCN circulars are also now available over Kafka. And this is what the schema looks like. So just all of the same content, except it's in JSON format and you can get it over Kafka. And two announcements from a while ago are that we have notices from Einstein Probe. Lots of folks are already receiving those, so you can see more documentation there. And also GCN circulars now support Markdown. So I'll do a quick demo of what that looks like. So if you're writing a circular and you want to include a table, just tap this Markdown button and tap that table button, and so it'll get rendered like a table. And in addition, you can cite other GCN circulars, cite papers by using DOIs, et cetera, lots of neat features. And we can actually parse all of this, any of these types of data or annotations that you put into the circulars are actually things that we can parse out and make available for computation. That's all.
Fantastic. And with that, everybody has stuck really well to time, so we have 1 minute left. Thanks so much for joining it. I'm just posted in the chat the form to fill out if you want to make presentations in future telecons. But with that, we will see you in about a month. Thank you so much.
Thanks, Curtis.